to tell you something.
Well, you have to promise me you won't tell anyone.
Promise? Promise.
Okay, so remember last semester I had this huge crush on a blonde guy who sat in the corner?
Who, Sebastian?
Yes, well, he asked for my number.
Shut up.
And we're going on a date.
Oh my god, I'm so happy for you.
But remember, you can't tell anyone. Look. Hi.
Hey, girl! How did your date with Sebastian go?
How do you know?
Everyone at school knows.
I'm gonna kill her.
But what?
Girl. You promised you wouldn't tell a soul.
What are you talking about?
Don't lie to me. Everyone at schools know about me and Sebastian.
I'm sorry. I couldn't help it. It escaped from my mouth. You know I have fugacity issues.
Stop using terms I don't understand.
Fugacity, the tendency to escape. Like in this case, the gossip just slipped out of my mouth.
I'm still mad at you though.
Let me make it up for you. Fugacity, Lesson 4. The word fugacity is derived from the Latin for fleetness, which is often interpreted as the tendency to escape. Fugacity allows us to model the behavior of real gases within the mathematical framework of ideal gas thermodynamics. Fugacity is the effective pressure for a non-ideal gas. The pressures of an ideal gas and a real gas are equivalent when the chemical potential is the same. Fugacity is equal to the fugacity coefficient times the pressure of the gas, in which the fugacity coefficient relates the non-ideal to the ideal gas pressure. For an ideal gas, the fugacity coefficient is 1 because the fugacity and pressure are the same. If the fugacity coefficient is less than 1, attractive forces dominate, meaning there is a less tendency for the substance to escape. Conversely, if the fugacity coefficient is greater than 1, the repulsive forces in the substance dominate, meaning there is a greater tendency for the substance to escape. In order to calculate the fugacity in the liquid phase, a reference state of an ideal gas is a poor choice. Instead, we choose what is called an ideal solution, which is a solution where all of the intermolecular interactions are essentially the same. The activity coefficient is defined as the ratio of the species fugacity in the liquid mixture to the ideal solution reference state fugacity. We use the criterion for vapor-liquid equilibrium, and by combining it with the fugacity and activity coefficients, we can calculate the fugacity coefficient to determine the vapor phase fugacity. In a real-world application, fugacity is used to determine the substances that conform a multi-component pollutant that has a harmful impact on the environment. Fugacity values can be read from standard tables, or they can be calculated using 3 different methods. The first method is concerned with the use of thermodynamic tables. First, we calculate the change in Gibbs free energy of the system, in which the final Gibbs free energy is determined with the conditions of temperature and/or pressure given. To calculate the initial Gibbs free energy, we determine the lowest pressure possible that can be obtained while leaving the temperature constant. Once our delta Gibbs free energy is found, we solve for fugacity, and from there we can calculate the fugacity coefficient. An equation of state, EOS, is an explicit function of the absolute pressure, the absolute temperature, and the molar volume of a pure substance or a mixture. Some EOS include: ideal gases have non-interacting molecules. As a result, the ideal gas equation, PV equals nRT, only applies for gases that behave ideally. The ideal gas law treats the molecules of a gas as point masses with perfectly elastic collisions. The van der Waals equation of state is a modification of the ideal gas law. The constant A corrects the intermolecular forces, while the constant B takes into account the molecular size. The compressibility factor Z accounts for the deviation of real gases from ideal gas behavior. When Z equals 1, the component is an ideal gas. Deviation can be positive if Z is greater than 1, or negative if Z is less than 1. The deviation is always positive at high pressure. The virial equation of state measures the deviation of a real gas from ideal behavior using its molar density. It expresses the quantity PV over RT as a power series in the inverse of molar volume. In this equation, B, C, and D are called virial coefficients. And these virial coefficients are different for each gas and are functions of temperature only. Finally, correlations use the principle of corresponding states, which says that the real temperature and the real pressure have identical factors of compressibility and deviate from ideal state. There are 2 methods, Lee-Kessler and Peng-Robinson. To use Lee-Kessler, the substance must be nonpolar, be of a single component, and be at a gas or liquid phase. However, if the conditions are near the critical point, it is not a reliable tool. On the other hand, Peng-Robinson is a reliable tool for natural gases and mixtures that are near the critical point, since it considers the intermolecular forces that are acting on the substance. The Clapeyron equation and its variants are used to modify pressure and temperature while maintaining phase equilibrium in a pure substance. Solid-liquid boundary, liquid-vapor boundary, Closius-Clapeyron, Antoine's equation. Thanks for watching. See you next time.